Hi, I am Nikola Korunovic.
And I am Nikola Vitkovic. We work at Faculty of Mechanical Engineering at University of Niš.
We will present you the webinar on testing as related to mechanical products, created as a part of ERASMUS project BRIGHT. Our colleague Sven Maricic from EURA University in Pula will also help us with the presentation.
You can find more details about the project and about the cases we demonstrate today at the following address. In real life, the word testing can have a lot of different meanings. It may relate to testing of new software or internet connection speed, or many other things.
Here, in context of biomedical engineering, testing means performing an experiment on a physical object, where the physical object may be a biomedical device, a part of this device, or a standard sample of material from which the device is built.
Let's now see the cases on which our demonstration is based. Before we demonstrate the three cases, let's have a short look at medical standards and testing methods. See why they are important and how they are used.
Hi, in this session we will say several information regarding the standards and quality control in medical engineering. As we said before in previous lectures, we can say that in order to officially manage any disease and on the other hand prevent it, we need to use some equipment. When we are using equipment, some certain standards should be applied towards that. Of course, third thing is quality control. Why quality control is playing important part? Because it is crucial to understand that lack of information regarding the maintenance of specific type of equipment can also lead to analyzing failures and different type of failures in this area. Quality, on the other hand, we can say, or we can define it as a group of qualities that a good or service contains, as well as the ability to meet the changing and sophisticated needs of customers. The set of characteristics and features that define and govern this use and the existence of these systems is represented by the quality of information systems. So, as we can see here on this slide, we have on first quality management system, which can be compromised if the certain information quality is not on certain level. To improve that, we can do several tasks. For instance, we can do some corrective things to prevent actions. Why? In order to prevent possible failures of equipment or some 3D printed part or part which need to be implanted, we need also to provide design control. Then we also have process and production control. During that stage, we also need to take into account the importance of this step. After we have produced a certain implant, instructional part, we can do post-production testing. Quality management system for medical devices, we can state it in 4 different types. Quality management, ISO 13485, which is stated requirements for regulatory purposes. Then we have software lifecycle 62304, for instance, medical devices software lifecycle processes. Then we have usability engineering 62366, medical devices software usability engineering process. In ISO 14971, medical devices risk management of medical devices. More automation, for instance, could streamline process like research, registration, protocol creation, storage, data collecting from design, etc., etc. Here we can also say that report dissemination, data sharing between the colleagues, data retrieval, etc., is also playing very important role. There has to be interoperability standards implemented so there is less variation in data and the systems used to store the data. If a colleague of yours is using one format which is not standardized, then the following approach needs to be taken into account. Why? Because without standardization, it is less achievable quality level. Systems that are simple to use and standardized are essential for creating a system that can be put to use by both data providers and secondary analysts. This is also playing an important part because some third part or some other organizations can also check the quality. Some of the quality activities can be also summarized on the diagram. We have documentation part, collaboration, as we mentioned before, special or certain requirements, and testing procedures. Of course, that are not all of key elements. Dimensions, for instance, product tolerances, material production, etc., is also important here. Constant collaboration includes information changes between all stakeholders, while it's also important that requirements be expressed clearly and without ambiguity. It is also important that they not contain too much detail, because going into too much details can also lead to misunderstanding, especially in different types of reports and when exchanging different types of system materials. Testing procedures for mechanical, chemical, and other specimen-related prerequisites describe under what conditions laboratory equipment and requirements we conduct empirical activities. In this diagram here, we can also see and notice lots of things and activities that needs to be taken into account before we start our quality assurance processes. In the following diagram, of course, we can see from risk analysis and preventive actions to planning process, verification, validation, which also consists user requirements, design input, design process, design output, which makes quality assurance process the product development process and phases, making testing prototype or prototypes, inputs according to user requirements, testing, assessing the result output, validation or validated layout according to user needs until it meets the requirement. Successfully validated design goes, of course, into production. Phases of medical device manufacturing we can put in 8 different stages. From the first concept through the plan, then we have design and development, prototyping, which can be provided by help of additive manufacturing, validation, technical documentation, technology transfer, and manufacturing. Of course, this is not straightforward process because from every phase we can learn and we can adopt several improvements. Keeping in mind all the safety and quality regulations as well as specialized standards that the product must have to be used in medical part when manufacturing medical device. There are several steps that must be achieved before manufacturing.
Let's now see why testing is performed in biomedical engineering and how is it performed. The first reason is to get the data that will help in medical device modeling. This may be done either by measuring the properties of a material used in device production or by measuring human body dimensions as a basis for device design. The second reason why testing is performed is to check the behavior of a medical device or of a prototype of this medical device. This may be done either by checking the dimensions of a produced medical device or by checking mechanical behavior of a medical device, for example, the relationship between force and deflection, or by checking the fit of a device on a patient, or by performing virtual surgery using a medical device and tissue prototype. Some important type of testing used in biomedical engineering, as featured in this webinar, are: first, mechanical testing. It means loading the specimen or structure on a testing machine and recording the response of the specimen. Then, 3D scanning. It means very accurately acquiring object geometrical data in 3 axes by means of either CMM, laser, CT, etc., as we will see later in more detail. And finally, simulated surgery, which means performing surgery on physical prototypes instead of living tissue. Let's say a few words about mechanical testing in general. There are two main reasons why mechanical testing may be performed. The first is to determine a material's mechanical properties which are independent of geometry. And the second is to determine the response of a whole structure to a given action. For example, to test the whole aircraft structure to destruction, or in our case, to test the whole medical device. Mechanical testing is usually performed in order to get mechanical properties of a material. Mechanical properties are physical properties that a material exhibits upon the application of forces. Examples of mechanical properties are modulus of elasticity, tensile strength, hardness, fatigue limit, etc. Obtained values of mechanical properties are used in simulation models of mechanical devices, and those are most commonly finite element models. Testing for mechanical properties are performed under various conditions, like tension, compression, elevated temperature, impact, or fatigue. One mechanical property that we just mentioned is the elastic modulus. It is the measurement of a material's elasticity. Elastic modulus quantifies a material's resistance to non-permanent or elastic deformation. It is defined as the slope of stress-strain curve in the elastic deformation region. One of the most commonly determined mechanical properties is the tensile strength. Tensile strength is the maximum tensile stress that can be induced in the material. By tensile stress we mean tensile force related to the initial cross-sectional area. Tensile strength is determined during the static tensile test, which is the basic and most common method of testing materials. The next commonly determined material property is the impact strength. Impact strength is the resistance of a material to cracking under dynamic loading. It is defined as the ratio of the work required to break a standardized specimen to the cross-sectional area of the specimen. There are two methods of measuring the impact strength: the Sharpe method and the ISO method. Another very important mechanical property is hardness. Hardness is a measure of a material's resistance to local plastic deformation. Local plastic deformation is formed on a small surface of the tested object as a result of mechanical pressing by a harder body called the indenter. Hardness is measured using 5 methods: ball indentation method, Vickers test, Rockwell test, Knupp test, and Shore test. Yet another mechanical property is compressive strength. Compressive strength is defined as the maximum stress that can be withstood by the specimen under the compression loads. It is determined by a test called static compression test. There, a sample is compressed between two flat plates using a force of a known value and recording the deformation caused by this force. As a final mechanical property, we will mention flexural strength. The flexural strength is the stress corresponding to the highest loading force obtained during the bending test. When these stresses are exceeded, the material is destroyed. Bending test is carried out by 3-point or 4-point bending with a constant speed on a prismatic sample on devices called benders. We have now seen what is mechanical testing in general. But how is it performed on medical products? Mechanical testing of a medical product, such as orthosis and prosthesis, includes 4 different areas. Those are dimensional inspection, mechanical tests, climatic tests, and durability tests. Let's now introduce some basic info on 3D scanning. 3D scanning is the process of analyzing a real-world object or environment to collect data on its shape and possibly on its appearance, like its color. The collected data can then be used to construct digital 3D models. We will now mention some of the 3D scanning technologies used in biomedical engineering. Those may be divided into contact and non-contact ones.
In contact ones, the most common are those based on coordinate measuring machines or CMM. Also, there are articulated arms. In non-contact technologies, there are 3D laser scanners and volumetric techniques. There are various types of 3D laser scanners, like time-of-flight, triangulation, structure light, modulated light, etc. In volumetric techniques, there are computed tomography or CT and magnetic resonance imaging or MRI. Those technologies are also very often used for diagnostic reasons. Coordinate measuring device is a measuring instrument used for spatial measurement of complex bodies, measuring its shape, length, angles, or so on. Coordinate measuring machines, or CMMs, are used to obtain 3D methodological form information on a workpiece and to estimate it. CMM are the most common measuring system used to assess the conformity of manufactured components with their geometric specifications. The good side of CMMs that they are also very accurate. 3D scanner captures multiple images of the object. Those images are merged into a 3D model, which is an exact three-dimensional copy of the object. Unlike 2D photos made up of pixels, a 3D scan consists of tiny triangles and polygons. Polygons form a polygonal grid that represents the geometry of an object with very good accuracy. X-ray computed tomography, or X-ray CT, is a technology that uses computer-processed X-rays to produce tomographic images. It is a very useful technology to get the information of the shape of the objects that are hidden inside the human body. CT reconstructions enable spatial and detailed view inside the patient and may be used to reconstruct geometry of organs. And finally, a few words about simulated surgery. There are basically two types of simulated surgery: computer-based, where technologies such as computer games production, three-dimensional graphics, virtual reality, and motion sensors are used to simulate the real situation. And physical, where artificial, often 3D printed organs, including fractures, tumors, and similar, are used to simulate and plan the surgery.
Our first case relates to personalized hand orthosis. It is used for stabilization of wrist or elbow injuries, making the healing process more comfortable.
In previous webinars, you learned how the orthosis was made. Now you will see how it was tested.
When fitting the orthosis to the hand, a padding material is used for a more comfortable fit. Then the two halves of the orthosis are secured together using Velcro tape.
Okej, spróbuj delikatnie odwrócić. Możesz ruszyć palcami?
In order to ensure that the orthosis allows for proper functional use of the fingers and that has a comfortable fit to the patient, several movement tests are carried out.
No i kończymy. Dobra, to tyle.
In order to mechanically test the orthosis, it first must be attached to the testing machine. Due to its personalized shape, a custom mounting system needed to be printed for the orthosis. Additionally, the orthosis is attached to a hand model before testing in order for the approximation to be more exact. The response of the orthosis is recorded in a 3-point bending test. You can see the relationship between the force and displacement on the diagram in the right corner of the screen. A maximum force of approximately 100 newtons has been achieved for the 3 mm displacement. For shiny surfaces, such as those of 3D printed parts, white paint can be applied to the model before the scanning procedure in order to prevent issues. Firstly, for the Shining Scan Pro 3D scanner, the scanning mode needs to be selected and a new project needs to be created. Next, the scanner is positioned straight towards the orthosis and the whole orthosis is fitted inside the recording area of the cameras. Now the scanning procedure can be started. After each scan is completed, the platform is rotated and the procedure is repeated until the user is satisfied with the acquired data. Every new scan is automatically positioned in relation to the previous scan, and the procedure is repeated. This is a time-consuming process, and because of this, the video here is sped up 5 times. Finally, multiple scans are merged in order to generate a triangle mesh. Upon inspection, visible artifacts are noticed, so additional scans are needed. The scanning procedure is repeated until a mesh of satisfactory quality is achieved. This model has less artifacts and is thus acceptable for quality check. Now, the final model can be saved. The GOM Inspect tool is used to check the dimensions of the 3D printed orthosis, 3D scan versus CAD model. First, a new project is created and the CAD STL model is imported. After this, the scan model is imported, and now, with both models loaded, they can be aligned. We are satisfied with preview and the 0.13 mm deviation, so the changes are applied. A comparison between the surfaces can now be made. In this representation, the green color defines the minimal deviations, while the red and blue define the positive and negative maximums. The extreme points are added manually in the regions of interest. In the end, a report with multiple views is generated for future analysis. This report can be exported as a PDF file.
Our second case represents a tan with tumor. This is a model which is 3D printed to help in pre-operative planning, that is, to simulate the surgery and help the surgeons prepare for it.
You will see one such simulation performed on the physical model.
The trainee or surgeon can get familiar with the specific patient case through the visual observation of the 3D printed model. Next, the incision path is planned and defined using a marker. Finally, the cut for removing the tumor is made using a scalpel. This process can be repeated multiple times until the best procedure has been selected, or for exercise purposes.
Finally, our third case is this face shield, a 3D printed piece of protective equipment. It was designed in the first days of COVID-19 infection to help medical personnel mitigate the spreading of the virus.
We will show you how it was 3D scanned to compare its dimensions with 3D CAD model and how it was tested for fit and strength.
Firstly, a compression test procedure file is loaded. Secondly, the face shield is securely mounted on the universal testing machine. During the test, the face shield can be deformed up to 40 mm before failure. In the left corner you can see the 4-stroke diagram. Finally, the results are saved in a native format and then exported as a CSV file for future analysis. The same procedures are repeated for the tensile test, during which the face shield is stretched up to 70 mm. This, combined with the results of the compression test, indicates that the face shield is highly adaptable to the width of a user's head. Due to the high gloss of the 3D printed plastic, the face shield is covered with a talcum powder in order to prevent issues while scanning. Firstly, a new project is created. Then the 3D scanner is calibrated using the calibration board and following the software instructions. For full calibration, 3 collections of calibration board data are needed. After the calibration board data is acquired for one orientation, the operator needs to rotate the board according to software instructions. This is a very important process for the accuracy of the final scan. For white balance calibration, a sheet of white paper is placed over the calibration board and 3 colors are projected onto it by an automatized procedure. Both camera views are turned on in order to properly set up the scanning procedure. Then the brightness settings are chosen so that the object can be seen clearly in the camera preview windows. Next, the number of turntable rotations is defined as 10 and the scanning procedure is started. The turntable starts to rotate as the scanner projects the raster pattern, while the acquired data is displayed in the software interface in real time. When the object has rotated one full circle, the scanning procedure has ended, and the results are displayed. If complete object data has not been acquired, the scanning procedure can be repeated in various object orientations in order to get the surfaces needed to fill the holes in the scan. Black or transparent objects can be used to assist in the positioning. Access data can be removed from each scan manually by the operator. The process must be repeated multiple times in order to get all the desired data. This is an especially difficult case for optical scanning, as the face shield can easily deform and thus change shape. If two scans won't align properly, manual alignment by joining three common points can be done. When we are satisfied with the results, the mesh model can be generated as watertight, closed volume, or unwatertight surface model. Additional model cleanup can be done with the mesh model by removing the excess polygons. Finally, the scan can be exported in the desired 3D model formats such as STL, OBJ, etc. The accuracy of the scan model can be checked with a vernier caliper measurement device by comparing scan dimensions with those of the real model. The dimensions can then be compared with those of the CAD model to determine the accuracy of a 3D printed face shield, as has been shown for the ortosis. The face shield has been tested on multiple users to confirm its ability to adapt to the width of a person's head. An additional elastic band can be used for a more secure fit.
Let's sum up the results of the test presented in this webinar.
Let's remember what was achieved in each of the three cases, what technologies were used, and what was their importance.
In case 1, the 3D scanning was used to obtain the shape of patient's hand, which helped in shaping the orthosis. Then, the fit of the 3D printed orthosis was tested to check its design and comfort.
Finally, the orthosis was mechanically tested to determine whether it would withstand the load that arise during its use.
In case 2, a 3D printed model of tangular tumor is used to perform simulated surgery, determine the best surgical procedure, and train the surgeon.
Finally, in case 3, a 3D printed part of face shield was 3D scanned to check the dimensions of the printed product in relation to the 3D model. Then, the fit of the shield on human face was tested, followed by mechanical testing, performed to test its strength in real application.
All demonstrated technologies have a very important role in biomedical engineering.
Further details on those may be found in links that are shown on the screen.
We wish you joyful exploration.
Just